Chapter 12 deals with sequences in series. What a sequence is just a list of numbers that follows a pattern. It is a function though, so it has a domain and a range. The domain is going to be the set of consecutive integers. So like the n, it would be 1 and then 2 and then 3 and so on, saying the first term and the second term and so on. The range is going to be the list of actual terms in the sequence. So we may see a sequence described as a function like this. A sub n is equal to 2n plus 5. And if we want to find the first term in the sequence, we denote it a sub 1, but all we do is plug in 1 for n and get 7. To find the next term, we plug in 2 and get 9. The third term, plug in 3 and we get 11. And we start to notice this pattern, which we should notice because it's a sequence. But we notice that we add 2 every time. So I'm thinking that when I get to the fourth term, it should be 11 plus 2, which is going to be 13. But let's check it out. 2 times 4 plus 5, yeah, it is 13. So then the fifth term would be adding 2 to 13, or getting 15. The sixth term would be adding 2 to 15 to get 17. So all of these numbers are the terms in our sequence. That makes up the sequence. Let's try another. We may see it written more like functional notation, but it's still the same idea. To find the first term, we plug in 1. 1 minus 1 is 0. Anything to 0 is 1. For the second term, 2 minus 1. 2 minus 1 is 1. Negative 3 to the first is negative 3. To the third term, we go negative 3 to 3 minus 1, and that'll give us 9. And we start to notice the pattern. Maybe I'm multiplying by this negative 3 every time. So I should expect to get a negative 27. And negative 3 to the 4 minus 1 is negative 27. So we're right. And to get the fifth term, the next term, we'd multiply negative 27 by negative 3 and get 81. And the sixth term then would be 81 times negative 3, which is negative 243. Describing the pattern is generally a little bit more difficult. Let's say we have 1, 4, 9, 16, and so on. And we want to describe the pattern. That means come up with the rule or the equation for it. Now, how I usually do it is just divide this up and then make a table out of it, where I call this one the first term, and this one the second term, and this will be the third term, and the fourth term, and so on. And what we want to be able to do is come up with an equation that relates these two numbers together all the way through. Okay? So we look at the first pair, 1 and 1. I said, well, they're the same. So maybe maybe my function is that a sub n equals n. So it would just be the same. But then as soon as we get to the second term, we realize a sub 2 is not 2, it's 4. And well, okay, 2 times 2 is 4, so maybe I just double it every time. And going back to the first one, if I double 1, no, that's not going to work. I don't get 2. So I think about some more ways the numbers are related, and 2 squared makes 4, so I go back and check it. Oh yeah, 1 squared makes 1, and 3 squared makes 9, and 4 squared makes 16. So yeah, our function is that I'm going to take whatever n is and square it. So now if I want to find out what the fifth term is, I just square it and we'll get 25. The sixth term would be 36. The seventh term would be 49. When we see something like 0, 2, 6, 4, 6, 12, things that jump out right away is like a 3. When I stare at this pile of numbers, I see a 3 because 2 times 3 is 6. 12's got a 3 in it, but then I quickly realize, hey, wait a second. 0 times 3 isn't 2, and 6 times 3 isn't 12. So let's see how we can break this up. This would be our first term, our second term, our third term, and our fourth term. And take a look at how we would make 0. Well, 0 is 0 times anything. 2 is just 1 times 2. 6 is 2 times 3. And 12 is 3 times 4. Okay, so I got 1 and 2, 2 and 3, 3 and 4. Maybe this one's 0 and 1. So 0, 1, 1, 2. How can we take this number, this n, and relate it to those ones? Well, going from 1 to this first number, that's 1 less than 1. And looking at this 2, going from 2 to 1, that's 1 less. 3 to 2, that's 1 less. So 1 less than n is just n minus 1. Now looking at the second part, 1 and 1, 2 and 2, 3 and 3, 4 and 4, that's the same thing. So there would be a function that would describe each term in our sequence. So if we wanted to find the fifth term, we would take 4 times 5 and get 20. For the sixth term, we take 1 less than 6, which is 5, times 6 and get 30, and so on. Now the word that goes with sequence is series. You often see these two next to each other, sequences and series. A sequence is the list of those numbers that follow a pattern. A series is what we get when we add those all up. Alright, so the sum of a sequence is a series. And we use sigma notation or summation notation to help us describe that sum. Now what sigma notation is first off, it's this big E looking thing. That's actually the Greek letter sigma. We use sigma to represent sum because they both have S's in them. Now, down at the bottom, you would see I equals some number A. I being the index of the sum, starting at some number A and going up to some number B of a function. Oops. And it wouldn't be a function in terms of n. It'd be a function in terms of I. Okay? So if we wanted to find the sum of the function 3 plus k squared, starting at k equals 4 and going up to k equals 8, this is how we'd have to do it. The first thing we do is we plug 4 into our function, so 3 plus 4 squared. Then we're going to move up to 5, 3 plus 5 squared. And we're going to keep doing this, 3 plus 6 squared, until we reach our top number, that 8. 3 plus 7 squared and 3 plus 9 squared. Oops. 3 plus 8 squared. And that's where we stop. We started at 4 and went up to 8, increasing by 1 every time. Now we just add up, find out what each of these terms are, and add them all up. So 3 plus 4 squared is 19. 5 squared is 25, so 28. 36 plus 3 is 39, 49 plus 3 is 52, and 64 plus 3 is 67. Now just add them all up, and we get 205. Right? So using sigma notation, we just start with that smallest number and plug it in and keep working our way up until we get to that top number. Sometimes we got to work backwards, though. Here we have the sum. Let's write the summation notation for it. So we're going to start with our sigma. And the thing we have to do before we can even really start filling this in is to look at our sequence. And our sequence starts with 25, 50, 75. So if we were going to write the function for it, a sub n, we notice it starts with 25 times 1 and 25 times 2, 25 times 3. So it's going to be 25 times whatever n is. That's my function that I plug in right here. Now, with an index of n, we started at 1 because 25 times 1 makes 25. But where do we end up at? And 25 times 10 makes 250, so that's where we would stop. And this would be our summation notation or sigma notation for that series. Let's say we have a bunch of fractions. Now, the thing about fractions that I always found helpful is to look at the numerator and the denominator separately. So if we're going to create our function a sub n, I'm going to look at the numerators first, and just the numerators go 1, 2, 3, 4, so the nth term is just going to be n. When I look at the denominators, 2, 3, 4, 5, the first term is 2, the second term is 3, the third term is 4, so that's always 1 bigger. Now that's going to be my function when I come over here and write sigma notation, that my function is going to be n over n plus 1. So my index, since I used n in this function, is going to be n. We started with n equaling 1, but where do we end up? And we notice at the end it just goes dot dot dot, and it doesn't really end. That means it's going to go on forever, and we use the infinity symbol for that summation notation.